Hello there, and welcome back on the LabHub. So in this lesson, we're gonna talk about work energy theorem and collisions. So we'll start with the collisions because this is the most important one, and work and theory theorem, it's not something useful and that you will use. The most important here is exactly collisions, because work energy theorem is just a part of collision. So we'll talk only about them. And at first, we need to know the difference between elastic and inelastic push or elastic and inelastic punch, no matter. So, elastic. We can call a punch, alright, or when two objects has a connection between them, we can call them absolutely elastic when total kinetic energy of both objects, is absolutely conserved. So if this ball has kinetic energy, right, around 100 joules, and this one has around 100 joules too, why not? So after the kick, they both keep the same kinetic energy. And we will use it in molecular physics, where we have a term called ideal gas. So these particles I just draw right here is a molecules of ideal gas. So in ideal gas, just a brief introduction to let you understand it better. So in ideal gas, each molecule, so each particle here, right, is absolutely elastic. So when two particles kick each other, they bounce back, conserving the whole kinetic energy, right? So we can show it in three cases, right? We got two same particles that goes in a same way. The second case, they kick each other, and here their kinetic energy equal 100 and kinetic equal 100, right? And the third case, right, 1, 2, 3, they are moving in the opposite direction with the same energy of 100 joules, right? So this is how the elastic kick works. But what about inelastic? Inelastic is, as you can see, is absolutely opposite thing. And a simple example of it is a collision of two cars, right? We got a car 1, we got a car 2. So when they experience a car crash, right, they're instantly stop. Or if this velocity 1 is greater than velocity 2, right? Velocity 1 is greater than velocity 2, so they will move in this direction and in opposite in another case. So usually if their velocity equal to each other, right, they will stop. And here is the formula that can be applied here. This is momentum of object 1 plus momentum of object 2 equal total momentum, right? Or simply m1v1 plus m2v2 equal m1 plus m2 times velocity final. And velocity final is sum of velocities in the system. Oh, sorry. And really important point here, is that in that case of absolutely inelastic kick or absolutely inelastic collision, right? If we're talking about it more scientifically, the mass of two objects unites into one scale. So after the car crash, in our case, m1 plus m2 equal to one exact mass of like one substance, right? So it's not a car 1 and car 2, it's just a few pieces of aluminum, I don't know, a few pieces of metal, just something. It's not a car 1 and car 2. And by the way, this is how sometimes planets work. So in early stages of planets, we got a planet, we got another planet, and they collide, and their masses are summing, right? So instead of two crashed planets and due to gravities, right, they're dividing into one big planet with the M1 and M2 inside it. So this is M3, the M1, M2, and this is not really exactly because sometimes some dust goes out in the context of a car crash. I don't know, a part of engine goes out, like, but this is an ideal case, right? So this is all you basically need to know about work energy theorem and especially collisions, because this is again the more important than work energy.